Welcome back to The Explainer. Today we're diving straight into a really fascinating collision between international policy and cutting-edge materials science. Look, we all know the world is facing a massive plastic pollution crisis, and for years we've essentially relied on two main avenues to fix it: global diplomacy to restrict plastic use, and scientific innovation to replace it. But what happens when the diplomacy just completely flatlines? Can a brand new molecular breakthrough in bamboo actually bypass a paralyzed international treaty? Well, we are going to explore exactly that. Okay, let's dive into this. Here is our roadmap for today. 1. The plastics treaty deadlock. 2. Why early bioplastics failed. 3. The bamboo plastic breakthrough. 4. Molecular engineering explained. And finally, 5. Bypassing the geopolitical gridlock. We're going on a little journey from global diplomacy all the way down to microscopic chemistry and then back out again. Section 1. The Plastics Treaty Deadlock. First up, let's look at the current state of global diplomacy regarding plastics, specifically what just went down recently in Geneva. Now, this number right here sets the stakes. 3 times. According to the UN Environment Program, if we don't make some major interventions, global plastic production is projected to triple by the year 2060. And because of that terrifying timeline, since 2022, the UN has been hosting these intergovernmental negotiating committee sessions called INC meetings to draft a legally binding global plastics treaty. The goal was to wrap this up by the end of 2024, but at the critical INC 5.2 meeting in Geneva in August 2025, the talks basically collapsed without a consensus. So why the gridlock? Well, it boils down to a fundamental divide in how to actually solve the crisis. On one side, you have the High Ambition Coalition. This is over 100 countries pushing for upstream interventions. That means legally binding caps on how much new, virgin plastic can even be produced and phasing out hazardous chemicals right at the source. On the flip side, you have the like-minded group, which is mostly made up of major oil and petrochemical producing states. Their stance is that the treaty should focus entirely on downstream measures, meaning better waste management and recycling without capping the initial production of plastics. Because the UN process requires consensus, this deep geopolitical and economic divide has essentially paralyzed the treaty. Section 2. Why early bioplastics failed. So, with policy totally stalled out, you might be thinking, well, why don't we just mandate a global switch to bioplastics? It sounds like an easy fix, right? But the hard truth is, early attempts at bioplastics have historically failed to scale effectively. And this brilliantly illustrates exactly why. When you stack conventional petroleum plastics up against the two most prominent bioplastics, PLA, which is polylactic acid, and PHA, polyhydroxyalkanoates, a really clear picture emerges. Petroleum plastic takes centuries to degrade, sure, but it is unbelievably cheap and easy to scale. PLA relies on food crops like corn and has moderate costs, but as we'll see, its degradation is super conditional. And PHA? It's truly biodegradable, even in the ocean, but historically it has been extremely energy-intensive and incredibly expensive to produce at scale. Basically, every alternative required a massive compromise. Let's look a bit closer at PLA, because it's the one you've definitely encountered the most. Think of those clear, supposedly compostable cups at your local coffee shop. Despite the reassuring little green leaf printed on the side, it's actually a deeply flawed solution. For PLA to truly break down, it requires sustained temperatures above 58 degrees Celsius in an industrial composting facility for weeks. If you just toss it in your backyard compost bin, or if it ends up in a regular landfill or the ocean, it's going to sit there for years, acting exactly like regular plastic. On top of that, it's brittle, it shatters easily, and crucially, it requires massive amounts of agricultural land to grow the corn to make it. That literally pits plastic production directly against the global food supply. Then you have PHA. It completely solves the degradation problem, but it introduces a whole new headache. A pivotal life cycle analysis by Garen Gross back in 1999 revealed a stunning irony. Producing pure culture PHA from corn glucose actually consumed more fossil fuel energy to run the sterile fermentation facilities than simply making standard petroleum-based polystyrene. So yeah, you get a biodegradable product, but the total carbon footprint and energy demand made it arguably worse for the environment. The bioplastic industry has been stuck between these unacceptable compromises for decades. Which brings us to Section 3, the bamboo plastic breakthrough. Researchers, notably a team out of Northeast Forestry University in China, realized they needed a completely different raw material, and they turned to bamboo. Bamboo is a rapidly renewable resource. I mean, this stuff grows incredibly fast, up to a meter a day in some cases, and it yields nearly 5 times more biomass per acre than timber. It doesn't compete with food crops, and it is wildly abundant. But the standout feature of this new material, which they call BM plastic, or bamboo molecular plastic, is this. It fully decomposes in natural soil in just 50 days. 50 days! There is absolutely no need for a 58-degree industrial composting facility. It degrades completely naturally and leaves zero toxic microplastics or chemical residues behind. Now, usually when you hear a plastic degrades that easily, you automatically assume it must be flimsy. But BM polyplastic actually rivals, or in some cases exceeds, many petroleum-based polymers. It boasts a tensile strength of around 110 megapascals and a fracture energy of 80 kilojoules per square meter. To put that into perspective, it is incredibly strong. We are talking replace solid steel pipe strong. Plus, it operates in a closed loop. It can be recycled multiple times while retaining roughly 90% of its original strength. And they pulled all this off without using a single drop of synthetic resin binder. Section 4, Molecular Engineering Explained. So, how on earth did they do it? How do you take a stiff, woody plant and turn it into a moldable, high-strength plastic without just gluing it all together with toxic synthetic resins? Let's zoom in on the molecular engineering here. The secret is in a very elegant, two-step chemical process. The main structural molecule in bamboo is cellulose, which naturally locks into an incredibly rigid, dense network of hydrogen bonds. That is exactly why bamboo stands up so straight and tall. In the past, scientists would just mash up bamboo fibers and mix them with plastic glues. But here, they take the raw bamboo cellulose and soak it in a deep eutectic solvent, specifically zinc chloride and formic acid. This solvent selectively dismantles those rigid hydrogen bonds without destroying the actual cellulose molecules themselves. Then, step 2, they introduce ethanol. The ethanol acts almost like a molecular conductor, coaxing those newly freed cellulose molecules to reassemble, but this time they pack into a completely new, denser, and highly ordered plastic configuration. So the crucial point is exactly this analogy. Think of it like carefully untying thousands of knots in a fishing net, rather than taking a pair of scissors and just cutting the net apart. They aren't breaking the bamboo down into mush and adding synthetic plastic. They are literally untying the bamboo's natural molecular structure and retying it into a plastic form. This is why it remains 100% bio-based, why it maintains such incredible structural strength, and why it can fully biodegrade when its life cycle is over. Section 5. Bypassing the geopolitical gridlock. Let's move to our final section and see how this micro-level science builds into a massive macro-level shift on the global stage. What does this scientific breakthrough actually mean for that deadlocked UN treaty we talked about earlier? Well, it means the market is moving regardless of the policy gridlock. And guys, this is not just a lab experiment anymore. Driven by China's aggressive bamboo as a substitute for plastic initiative, these materials are scaling up rapidly into real-world applications. In Fujian province, local companies producing bamboo fiber tableware saw exports jump 35% year-over-year in 2025. Over in Sichuan province, they are literally replacing steel and cement in urban water and sewage systems with bamboo-wound composite pipes. And in Tianjin, a drone just completed its maiden flight using a bamboo composite fuselage that is 20% lighter and roughly 75% cheaper than carbon fiber. The commercialization here is happening at an absolutely blistering speed. Now, here is the geopolitical reality we have to acknowledge. While the European Union, Japan, and the US are heavily funding research into various biopolymers, China holds a massive structural advantage when it comes to bamboo. They control roughly 70% of global bamboo exports. They have the largest bamboo forest area in the world, and they have decades of built-up processing infrastructure. If BM plastic fully scales from the laboratory to global commercial production, China is positioned to completely dominate the next generation of industrial materials. Which brings us to the core question you should really take away from this explainer today. With international diplomats totally deadlocked over whether to cap petroleum plastics or just recycle them better, this science has fundamentally shifted the playing field. When you have a material that is as strong as plastic, fully biodegradable in 50 days, and backed by a country with a near monopoly on the raw resource, will technological innovation and molecular engineering ultimately bypass the deadlocked UN policy consensus? Will science actually solve the plastic crisis before global diplomacy even manages to agree on the rules? It is a fascinating paradigm shift, and for sure, one we'll be watching incredibly closely. Thank you for joining me for this explainer, and as always, keep questioning the materials that make up our world.